So one aspect that we investigated was how does the month-to-month variability in significant tornado predictability manifest itself in these conditional probability curves. And so we're going to now disaggregate this data set and the conditional probability curves into month by month. And I'm going to show two separate groupings, November to May and then June to October, and we're going to take a look at how these conditional probability curves vary relative to the full data set over here, conditional probability curve in black. All right, let's start with November to May first, and you'll see in just a moment why we're grouping it like that. You can see for the month of November over here, conditional probabilities of significant tornadoes do increase notably with higher STP values, suggesting a relatively strong practical relationship between STP and significant tornado occurrences. Now, December, relatively weak practical relationship here. We're going to be grouping this in with these other months in order to maintain continuous period grouping over here. Let's go to January, see that strong practical relationship between STP and significant tornado environments, significant tornado occurrences with that slope that's noticeable here going into February, March. As we're dealing with smaller sample sizes over here, a bit of noise, those are relatively less common into the March period. But where we see the critical mass of actual sample sizes in this vicinity over here, we see noticeable slope that is especially accentuated into the month of April, suggesting strong practical relationship between STP and significant tornado occurrences, and same general idea here in May. Now let's go to the June to October period, so going into some of the more weakly forced times of the year, more of the warmer season, into the heart of the warmer season. There's a different character, different behavior to what the SCRAM system produces in terms of these conditional probability curves. Looking at the month of June, you can see that those initially sloped curves in November to May now flatline. They appear to collapse over here, suggesting relatively weak practical relationship between STP and significant tornado occurrences in June. This is repeatable mostly in July, especially August, September as well. You can see largely a flatline curve here, and October as well. This period of time when we have a weak practical relationship between STP and significant tornado occurrences. Based on this and the attempt to have continuous clustering based on the differences in the predictability behavior, we are now going to focus on November to May versus June to October in terms of evaluating the predictability of significant tornadoes. November to May, we see a stronger practical relationship between STP and significant tornado probabilities, and then June to October when that relationship appears to be relatively weaker using the SCRAM system. Now let's take a look at what happens when we take those initial significant tornado probability full SCRAM conditional probability curves and then disaggregate that into a November to May component, which is shown in green over here, and then in dark maroon, June to October. You can see some pretty substantial differences overall in terms of significant tornado probabilities. Compared to November to May, in the green curve over here, where we have a noticeable slope, the June to October significant tornado probabilities fall substantially, generally by a factor of around 5 to 10. In terms of the downstream significant tornado probabilities, with little to no variability in the June to October time period amongst the various ranges of STP values. And this is somewhat counterintuitive in terms of these results that we're seeing from the SCRAM system. So we wanted to look more at what do the individual components of STP how are those manifested in terms of variations in predictability from November to May compared to June to October? We'll look at buoyancy-related variables, stability-related variables here, starting with mixed layer CAPE in the top panel, November to May in green. You can see at least a modest predictability signal here in November to May for ML CAPE, modest at best for mixed layer inhibition overall, that in both cases show a major collapse flatlining as we go to June to October. And this is suggesting the components offer decreasing predictability going from the more strongly forced November to May period to June to October. Now, we're looking at some of the kinematic-related variables, effective storm relative velocity, as well as effective bulk shear. We see a relatively similar trend as well, with those steeper slopes depicted by effective storm relative velocity for November to May, as well as that for effective bulk shear, to largely decrease in probability and flatline in general for November to May compared to June to October. So collectively, these results are showing using SCRAM that there's a decrease in the forecast utility of the diagnostic variables used in assessing significant tornado potential from November to May to June to October time period. Now, we're going to show one example over here that could illustrate this particular case. This is July 13, 2015. I think pecan may have been out here. Dave, is that right? Yes. Western Indiana, Eastern Illinois, general vicinity? That general area over here. You can see, based on SPC mesoanalysis, very high values of STP. We had sustained organized supercell storms within that particular environment. Yet the only significant tornado of the day in this particular case occurred farther to the west in Kansas, in the vicinity of a frontal zone with large amounts of ambient vertical vorticity, deep boundary layer all the way back there into central Kansas, much lower STP values, and that's where the one significant tornado of the day occurred. Now, I do want to mention a caveat in this image. There was a special sounding from central Illinois released, and it was actually showed a major drop-off in mixing ratios above the ground, suggesting that locally there's some question about the validity of these STP values. We don't have a lot of observations to affirm these particular values. There's some question offered by one of the special soundings in central Illinois. But regardless, this is the gold standard that we have for mesoanalysis and the threat assessment of severe weather. And so it's important that we pull this information together with SCRAM system in terms of using this as the foundation for threat assessment and working with what do these values mean. Now, we've identified certainly a challenge in significant tornado predictability, forecasting going from from November to May to June to October, and I have a bunch of hypotheses listed here. I'm not going to read all of them. I'm going to mention one example, for instance, the parameter components of STP, various parts of STP could offer relatively limited representations or have some issues with providing representations of significant tornado potential in June to October. For instance, the weighting of ML Cape could be too high, which is a relatively more ubiquitous quantity in the summertime. Lightning also might not be a good proxy for supercells in June to October compared to equivalent November to May environments as well. Ultimately, we have a lot more to learn about significant tornado forecasting. And these hypotheses could provide some steering, for instance, in terms of what additional research we could use in terms of short-term significant tornado forecasting, and particularly dealing with some of the lack of predictability as we're looking at the June to October period. I'm going to show how we're going to shift gears now that we've looked at significant tornado forecasting issues there and looked at the SCRAM system. We're going to actually apply this now to a real-time forecasting example. Let's go back in time to a few weeks ago, October 6th. You may remember a few tornadoes, perhaps even several tornadoes occurring in parts of Kansas, north central Kansas, southeast Kansas. We're going to look at how the various parameter values as forecasted in the NAM correspond to conditional probabilities of tornadoes using the SCRAM system databases collected from 2006 to 2014. And we're going to start out by looking at what actually happened in reality and then go back retroactively and consider what the forecast looked like based on SCRAM output run on the NAM. All right, so looking at the setup here is a water vapor image showing a mid-level dry slot extending from parts of the southern Rockies into the central Great Plains. Within the moist conveyor air with a history of ascent over here, seeing relatively isolated to widely scattered convective areas from parts of southwest Oklahoma to eastern Kansas, peripheral to that mid-level speed max. At the surface, some boundaries that have placed over here overlaid on surface observations and a visible satellite image at 2045Z. I've analyzed here a surface front extending from central Kansas to northeast New Mexico, the quasi-stationary boundary northeastward into parts of central Iowa, intersecting the surface low pressure attendant to that baroclinic zone. A prefrontal trough extends southwestward into northwest Oklahoma, with the dry line intersecting it in south central Kansas. To the east of that dry line, very moist, stable conditions existed across Oklahoma, whereas the buoyancy was limited to some extent across parts of eastern Kansas and western Missouri by convective outflow related to ongoing, previous convection from the overnight hours into the morning, depositing this outflow boundary that I've analyzed here from southern Missouri into southern Kansas with active occasional supercell clusters and some tornadoes affecting parts of southeast Kansas. Within a narrow corridor of air mass recovery immediately to the east of the prefrontal trough axis and dry line, where you can see some degree of back low-level flow relative to surface winds to the west of the dry line / prefrontal trough. We are developing a relatively favorable but narrow corridor of good environment for potentially tornadoes to occur. You can see, based on the wind profile here observed at Topeka, favorable wind profile for supercells with ample low-level helicity present in the sounding, although you can see Topeka was deeper into the cool outflow convectively contaminated air, such that there was still much remaining convective inhibition there on the Topeka sounding. Regardless, we had a good wind profile such that storms that developed along that prefrontal trough corridor axis were able to attain semi-discrete to supercell cluster modes for at least a short amount of time, with mid-level flow vectors oriented at least semi-obliquely to the initiating boundary, and we actually got a number of tornadoes occur in this particular setup. So that's what actually happened. But let's see how SCRAM could have been used in terms of a 30-hour forecast. I want to make it clear we're using the SCRAM database in terms of all those probability distributions applied to the NAM. And we need to use some background output variables in order to say something about what those probability distributions actually look like. And so any issues with the NAM biases are going to be represented in terms of probability variations in the SCRAM output. Now, in terms of how, and I want to indicate this map over here, I'm going to explain this, is very experimental. This is internally developed by John Hart. This is in its infancy overall in terms of taking these large sample size distributions and then applying it to actual forecasting, what the probabilities correspond to in real time or in a forecast mode. And in order to do so, and to combine various parameters together, we have to make choices about what variables could describe the phenomenon that we're trying to forecast. And so this is going to involve the process of expert elicitation, where we're going to be considering, based on the experience of forecasters, years, decades of experience of forecasters, what parameters would most suitably explain the phenomena that we are trying to forecast. And we have a list over here, and ultimately, this list over here, don't worry about it's all small font over here. It's going to change a lot as we test this data set. It's going to change a lot as we evaluate what's going on. Don't worry about the details again, but we're looking at different combinations of variables that we can pretty much dissect or sub-bin and then combine those together to make those probability distributions using the 2006 to 2014 data set, and then determine, based on the output from NAM mesoanalysis, what did the conditional probabilities look like, so that if we have some forecast of thunderstorms or we know that lightning is ongoing, we can make some threat assessment in terms of downstream severe weather. And this corresponds to, again, a 30-hour forecast for any tornadoes using the SCRAM database, and this set of parameters over here, 30 hours into that day in which we had multiple tornadoes occur across parts of eastern Kansas and vicinity. As you can see, relatively high values here, over 10% within a corridor from northeast Kansas into southwest Iowa. Relatively broad area of at least modest probabilities extending all the way from northern Oklahoma into northern Illinois. And we also have overlaid here model QPF, convective QPF in the blue hatched areas to see where that conditional part might effectively come to life in terms of manifestation of thunderstorms interacting with this environment to actually make those conditional probabilities real. You can see an overall dearth of QPF, convective QPF signal within the higher SCRAM-based higher SCRAM-based conditional tornado probabilities. However, we know that some of the model QPF, there are a lot of issues involved in terms of the accuracy of those fields, and acknowledging some attempt for, or acknowledging some potential for the development of thunderstorms within the western corridor of the higher conditional tornado probabilities using SCRAM would certainly lend concern in terms of tornado threat into parts of northeast Kansas. So there's a very strong signal here, very helpful. And granted, into Iowa, we see a tendency for the SCRAM probabilities to be too high. That's largely because we're dealing with a NAM background here, which over-destabilized boundary layer conditions into portions of Iowa in this particular case. All right, so already we've been looking at some of the preliminary verification of the SCRAM system using various combinations of variables that describe certain convective phenomena in terms of convective hazard phenomena. And we're effectively going to look at different periods of time within the database, 9-year samples, to develop these learning data sets effectively, develop probability distributions for the various severe convective hazards based on 9-year sample sizes, and then test it on one remaining year. Now that we've gone through 2015 and we're well into 2016, we'll be able to bring in 2015 into this analysis here. So for instance, in terms of developing an evaluation program here, we'll consider 2006 to 2014 samples in terms of generating downstream probability distributions for downstream severe. And so effectively we'll create all those distributions that we showed earlier, multiple dimensions as we consider different combinations of parameters involved. And we'll then test those probability distributions effectively on the remaining year. In this case, what I'll show shortly, 2015, as an independent sample to serve as this evaluation case. And then we're going to show right now in a reliability diagram to see how well SCRAM was able to depict what I'll show here, any severe in thick purple over here, tornado in red, blue severe wind, and green hail. Along the y-axis here, we have observed frequencies, forecast from SCRAM shown along the x-axis here. So every single point where the forecast is equal to the observed frequency, that represents reliability. That's plotted as the reliability line that's dashed here, y equals x, effectively here. And the goal is to have a system that reproducibly gives us hovering values along y equals x. That's what we'd like to see. If we have a tendency to be below this line over here, for instance, it would be represented by a systematic over forecast of a given severe convective hazard. And this is exactly what we'd like to see, suggesting a very reliable system here with the bulk of these curves largely hovering around y equals x, particularly for the forecast probabilities where we have much larger sample sizes. We get to very high forecast probabilities. We don't see those come up every day, fortunately. And so where we actually have the critical mass of the sample, we're dealing with a very reliable system here with those various severe convective hazards largely hovering around y equals x. All right. Now let's wrap this talk up here with several conclusions. As we talked about here, we've created and explained a system for pairing environmental conditions, environmental information, with severe storm occurrences into the future, specifically looking at 2 hours into the future. This incorporates both severe report as well as null occurrences related to a grid box with lightning occurring in them and certain environmental characteristics, where we're investigating the ability for the diagnostic parameters, environmental conditions at those grid boxes with lightning, to potentially explain future severe storm report occurrences in a prognostic manner. This could very much be used in terms of useful for one-on forecast initiatives as well as facets initiatives, trying to look further out from just a warning time scale, for instance, that we have right now in the legacy system in terms of severe weather threat going out to multiple hours into the future. We were able to show through the data set that MU CAPE and especially effective bulk shear were very useful in terms of anticipating severe hail and wind, especially for effective shear. We found that severe wind tends to occur more frequently with weaker values of effective shear for increasing values of buoyancy. We found that tornadoes occur within an optimal range of ML-LCL values, although we see relatively consistent, relatively low flatline probabilities for tornadoes corresponding to various ranges of ML-LCL for surface-based organized convection. We were able to see that using the SCRAM system, STP and its components offer more predictability in November to May, with relatively less predictability in the June to October period. This certainly encourages additional research in terms of investigating some of the seasonal variability in the predictability of significant tornadoes, especially with some of these results shown by the SCRAM system. And ultimately, a major avenue down the road is to continue to develop applications of SCRAM in terms of combining it with numerical weather prediction, model output, mesoanalysis data in terms of contextualizing those environments depicted by mesoanalysis NWP in terms of explicit probabilities of severe convective hazards. And this is ongoing work that you got to see a sample of earlier that's under internal evaluation right now. hopefully down the road, this will be something that we'll be able to look at in terms of evaluating short-term severe convective hazard threat assessment.